this video we'll do the free responses for chapter 7. And we will start with 2009 number 2. I'm noticing I didn't number the pages in y'all's packet, which is bothering me. I keep going to say what page number we're on, but there is none. But anyways, so in this problem it says a tire manufacturer designed a new trend pattern for its all-weather tires. Repeated tests were conducted on cars of approximately the same weight traveling at 60 miles per hour. That's just saying they're keeping all their confounding variables the same. The test showed that the new tread pattern enables the cars to stop completely at an average distance of 125 feet with a standard deviation of 6.5 feet, that the stopping distance are approximately normal, and the stopping distance are approximately normal distributed. So they're telling you the mean is 125 and the standard deviation is 6.5. So what is the 70th percentile of the distribution of stopping distances? So they're just asking what stopping distance would be at the 70th percentile. So you just use the distribution they gave you for your sample. Wait, no, not sample. For your population. Oops, 6.5. So we draw our distribution, and to be at the 70th percentile, go ahead and put my mean. It would be what value gives 70% area below. We're looking for this value right here, with the area equaling 0.7. So how do you find a value given the area? We use inverse normal. And we would type in that area of 0.7. The mean is 125, and the standard deviation is 6.5. And if you type that in your calculator, you should get 128.4, and that is the value down here, so it's in feet. The stopping distance of 128.4 feet is at the 70th percentile. And if you wanted to give a reasoning, because 70% of observations fall below 128.4 feet. Okay, so then part B says, what's the probability that at least 2 cars out of 5 will stop in a distance that is greater than the distance calculated in part A? Okay, so if we think about this, it sounds to me, when I read this and it's probability of getting something out of a certain amount, to me that rings binomial, right? So if I think about my bins, to make sure, bins is what, just success and failure. So what would your success be? What's the probability that will stop at a distance that's greater than the distance calculated in part A? So what's the probability of being greater than this 128? So success is being greater than 128 feet, which means the failure is not greater or less than or equal to 128 feet. Each stopping distance should be independent, so that should be a check. Fixed number of trials, how many are we talking about out of 5? So your n would be 5. And now what is our probability of success? So we'd have to actually find this. What is the probability of your observation being greater than 128? Because we did less than 128. So how could you find that? If all this area should add up to 1, right? So if there's 0.7 below, what's the area, the probability of being greater? It should be 0.3. So if you wanted to actually do normal CDF, you could, and do your lower bound is 128, your upper bound is, I should be doing 0.4, not just 128. I don't know why I rounded it. But it would be a lot quicker to think, well, we know there's 0.7 below, so it should be 0.3 above. Should add up to 1. And again, I don't know why I rounded this. Make all those 0.4. So we should be good to go and do binomial. So we're going to do binomial. And now is this going to be PDF or CDF? If it's, what's the probability that at least 2? That would be CDF. Because let's go ahead and write the probability we're finding. That would be the probability of x being at least 2 is greater than or equal to 2, right? If you're at least 2, you can equal 2 or anything greater. So now we should be good to go. We go to binomial CDF, distributions, CDF, the number of trials should be 5. Probability of success we got here is 0.3. Lower bound if you're at least 2 equals 2. And the upper bound is your however many trials, the max is 5. So it's 0.4717. So let's write down n equaled 5. Probability of success is 0.3. Lower bound is 2, and the upper bound is 5. And so that probability equals 0.47, I'll round it up to 2. And is that all it asks for? Just what's the probability? Yes, so that's your answer. Okay, last one says, what's the probability that a randomly selected sample of 5 cars in the study will have a mean stopping distance of at least 130 feet? So if you notice, we're saying, what's the probability of not having a stopping distance of 130? It's saying, what's the probability of your sample having a mean stopping distance? So what's the probability of your sample mean, x bar, being at greater than 130. We could do equal to for normal CDF, it's not going to change it. So if we think about this, we have to talk about what's the probability of getting a sample result. That is where you use your sampling distribution. You cannot just use this population because this is just the probability of getting x, one result. We want the probability of getting x bar. So we got to create a sampling distribution for x bar for what given sample size, n being equal to 5. So because your population was normal, we know our sampling distribution is going to be normal. We don't have to check any theorems. Now how do we know the mean of x bar? It equals the true mean. Maybe I should be showing all the formulas. So when we create a sampling distribution, we're on the back of the formula chart. And the mean of one x bar is equal to the true mean, and the standard deviation of x bar is the standard deviation divided by square root of n. So the true mean for your population was 125, and the standard deviation of our sampling distribution will equal the true standard deviation divided by square root of n. Oops, why did I put that there? So in this case, that would be 6.5 divided by the square root of 5. So if you type that in your calculator, that is 2.907. So now this helps us. We have our distribution, we have the mean, the standard deviation. So it's still centered at 125, but the standard deviation is different. That's what's going to mess you up if you just use the original setup. And we want to know what's the probability of having an x bar value of at least 130. So you put 130 and you shade greater than. And that 130 is x bar. That's why we labeled this down here. This was just labeled x. So to find that area, that probability, we're going to do normal CDF. The lower bound is 130. The upper bound is infinity 9e999. The mean of your sampling distribution is 125, and the standard deviation of your sampling distribution is 2.907. And if you type that in your calculator, you should get 0.043. So that's the probability of getting our sample result of 130 or something greater. So hopefully this makes sense on the difference. I really am trying to harp on the difference between the original population distribution and the sampling distribution. The standard deviation should be getting smaller as your sampling distribution sample size increases. Okay, so let's go ahead and do the one on the back. So this is 2007, number 3, and it says, Big Town Fisheries recently stocked a new lake in a city park with 2,000 fish. The distribution of the lengths of the fish is approximately normal. And so it says, Big Town Fisheries claim that the mean length of the fish is 8. If this claim is true, which of the following would be more likely? A random sample of 15 having a mean length that's greater than 10? Or your random sample of 50, when n is 50, having a mean length greater than 10? So what is it wanting you to think about is, what is changing the sample size going to do? So we're going to come down here, and as soon as you notice that that's what it's doing, is changing the sample size, you should think about, what does that mean for your sampling distribution? Right, because that's what we're talking about, the sample distribution for mean, but the difference is 15 versus 50. So when you create a sampling distribution, they're both going to be centered at the true mean, which is 8. But what is changing the sample size going to do is it's going to change the variability, right? A smaller sample size has greater variability, greater range. And so then this, since it's a greater n, it should have smaller variability. So I'm going to try to draw this on the same distribution. So greater variability means it goes out in the tails more and it's going to be flatter. That would be n equals 15. And then if you do n equals 50, it's going to be skinnier and narrower. Maybe not that drastic, but so you can see the difference. So then which one is going to have a greater chance of having a mean length of 10? So if you think about 10 is going to be over here, depending on the standard deviation, but that, and you're going greater, so you're going into the tail, right? So red, that's going to be a small area for 50. Now for green, for n is 15, that's going to be a lot more area. So which one has a greater chance would be the smaller sample size, because it has greater variability, so it has more chance of being out in the tails. Hopefully that makes sense, so we're just going to put that in words. The sample size of 15 would have a greater, how did it word it? Probability of having a mean length greater than 10 because the smaller sample size has greater variability, therefore greater area in the tails. And that should suffice. As long as you associated a smaller sample size is going to have more variability, so that's going to have a greater chance of being greater than 10. So for part B, it says, suppose that the standard deviation of a sampling distribution of a sample mean of random samples of size 50 is 0.3. Okay, so right there, let's think about what that's saying before we even read anymore. It says the standard deviation of the sampling distribution for a sample mean. So that's giving you the standard deviation for the sampling distribution of the sample mean, means that's giving you standard deviation of x bar. For a random sample of size 50 is 0.3. So if you notice, they're giving you your sampling distribution standard deviation. So you're not going to have to go use this formula because they gave you that value. They didn't give you the population standard deviation, they give you the standard deviation for your sampling distribution. So you don't need this formula because they gave it to you. So be careful on the wording there. So then if the mean length of the fish is 8, so the mean is 8, which means we know the mean of our sampling distribution is equal to that true mean, so it's also 8. Use a normal distribution to compare the probability that a random sample of 50 fish, which matches our sample size that we have our information on, will have a mean length of less than 7.5. So what's the probability of getting this sample result? So it's asking what's the probability of getting an x bar less than 7.5. So if we set up our distribution, said use normal, the mean of our sampling distribution is 8 and the standard deviation is 0.3, and we want to know what's the probability of being less than 7.5. So that area is going to equal normal CDF. The lower bound would be, negative 9E999. The upper bound would be 7.5. The mean of the sample, because this is a sampling distribution, is 8. And the standard deviation of our sampling distribution is 0.3. And if you type all that in your calculator, you should get 0.0477. So that is this probability of getting a sample mean of less than 7.5. And for part C, it says suppose the distribution of the fish lengths in the lake was non-normal, but it had the same mean and standard deviation. Would it still be appropriate to use a normal distribution to compute the probability in part B? Justify your answer. So this is asking about your conditions. So let's say it's saying you didn't know that the population was normal, that it was non-normal. Could we still use a normal approximation for the sampling distribution? So if you go back to what we said for chapter 7, we're talking about a mean sampling distribution. The sampling distribution can still be normal if it follows CLT, if our sample size is greater than 30. So because our N is 50, by central limit theorem, our sampling distribution will still be normal even if the population was non-normal. So that's what we're going to write out. I'm going to go ahead and rewrite down for this part that my N equals 50. And I'm just going to write it out in a sentence. So because N is greater than or equal to 30 by central limit theorem, or you could probably write CLT. Let's see if I can just answer the question. By central limit theorem, normal distribution would still be appropriate. And that should suffice for that one. It's just checking that you know that condition. So let's say this was a proportion problem where it was sampling distribution for p hat, then you wouldn't use central limit theorem, you would use large counts, and you would show these two facts. So just keep that in mind. And that is it for those. So let me know if y'all need anything as you're working on these questions and your AP assignment.